That's perfect. So great. So now for something different, and we know have a talk about tactics in Mathlete by Vasilii Nesterov, who is a grad student at CMU, and we are very happy to have him work on this real asymptotic tactics that people have been hoping for a very long time. So tell us about it.
Yeah. Hello, everyone. Thank you for the introduction and for the opportunity to speak. So, I'd like to tell you about the project I've been working on over the last year. This is a tactic called compute asymptotics. And the purpose of this tactic is to prove goals like this ones you see on slide. For example, it can prove that this function tends to this limit at infinity. And also, for example, it can prove that some function is big O of the other function. So I'd like to present the algorithm that is used in this tactic. And I think it's interesting because of two reasons. The first reason is that I think many people, while studying limits, they feel that computing limits is quite mechanical work, but it's not that trivial to come up with an actual algorithm for that problem. And the second reason is more lean specific. This algorithm I'll be describing heavily relies on lazy computations. And to formalize them, we would naturally wanted to use co-inductive types, which lean type theory doesn't have. So this leads to many technical difficulties I'd like to share. And I think it's one of the first, let's say, big projects in Lean that relies heavily on co-induction. Yeah, and I must say that my work is far from being original. I mainly I was following the paper by Manuel Eberl, who implemented similar tactic in Isabel. So let's begin. Let's state our problem. Suppose we're given a function, a real value function, as a syntax tree. So, for example, as an expression, but this doesn't matter here. And we want to compute its limit at plus infinity e, and we want to prove we're correct, right? As in many other tactics, implementation consists of two main parts. The first part is to develop some theory, and the key object in this theory is multi-series. So this is a generalization of asymptotical expansions, but the idea is to have something we can compute with, and that at the same time, in some sense, approximates our functions. Then we define operations on this type on multi-series by mirroring operations on functions, and prove theorems like this one you can see on the slide. For example, if f as function is approximated by some multi-series, which I also denote f but with beautiful letter, and g also approximated by some multi-series, then their sum is approximated by the sum of this multi-series. And using the theory, when we're given a function f, we construct a multi-series that approximates our function, and then we extract its leading term, whatever it means. And our theory allows us to conclude that the limit of f can be computed by inspecting this leading term. So this is high-level idea of how this tactic works. And in this talk, I will be mainly covering the first 2 points in the theory, because firstly because of the limited time, but also because this is where difficulties connected to co-induction and co-recursion arise. So let's start with defining multi-series. before that, we need to define a basis. Basis is just a list of real functions. And a typical example of basis, you can see it on the slide. And when we have a basis, a multi-series in this basis is just a formal power series of monomials constructed from these basis functions. And also, I must note that here we allow exponents to be any real numbers. So, for example, this would be a correct multi-series. Then we need to impose some constraint on our bases. So basis must contain the identity function. So we are able to express just function fx equals x, right? All basis functions must tend to plus infinity. And the last condition is that the basis is ordered so that logarithm of the next basis function is little o of the logarithm of the current basis function. We need the last property because it allows us to asymptotically compare any two monomials by just comparing tuples of their exponents in the lexicographic order. And yeah. So the next question is how to represent our multi-series type in Lean. The first idea here is to isolate the first basis function and view multi-series in basis b1 dot bn as a univariate series in b1 whose coefficients are also multi-series but in the tail of the basis. So we use so-called nested representation of this object. And we define the type in Lean as follows. So we do recursion on basis. If basis is empty, it's just real numbers. All right. If we don't have any basis function, we can express only real numbers. And then if the basis is not empty, we define it using the seek type. Seek is not widely used. I think it's like list, but it allows possibly infinite lists, right? And this list contains pairs. The first component of each pair is just exponent of the term, and the second component is coefficient, right? So again, a multi-series in the big basis, b1 dot b2 bn, is just a list of monomials with real exponents and coefficients of the type prems bs, where bs is just a tail of our basis. Right, and here we have pre because we will add an extra constraint to call this object an actual multi-series. And I'd like to introduce some notation I'll be using through this talk. So I'll use regular letters for functions and beautiful letters for multi-series. And when I reason about multi-series as a list, I'll use doubled brackets. Right? In this notation, C is just a multi-series in a smaller basis. This is a coefficient. E is an exponent, so the first component in this pair, and F is the tail. All right, so this is basically nil and cons well-known operations for lists. Let's move on. The additional constraint is sortedness. So we want our multi-series to be sorted in the sense that, for example, here E1 must be greater than E2, E2 must be greater than E3, and so on. And this is a recursive definition, so we want all coefficients, which are also multi-series, to be sorted as well. Why do we need that? This allows us to extract the leading monomial of a series which we are interested in as just its first term, right? Because the next term would have a smaller exponent, and then this is asymptotically smaller. All right. And then we need to define some operations on multi-series. The first two operations is addition and negation and addition, and all these definitions will be like this. So we define this in a empty basis, just by using operation from reals. So for example, here we use negation from reals. Then we have to deal with empty multi-series. We leave it as is, of course. And the only interesting case is the last one. So here, when we want to compute a negation of cons, right, we must push the negation into coefficient here and into the tail here. I hope that it's morally clear that these equations define define some function, right, on multi-series. But there will be a problem to convince Lin that this is a correct definition. I'll speak about it in a minute. Let's before that let me define an addition. Right, here we have three edge cases which are not interesting, and the last case is when both terms are conses, right? So this looks scary, but the meaning here is very simple. When we add two multi-series, what we need to do is to merge them like we merge lists in merge sort algorithm while maintaining the correct order on exponents. So for example, if E1 is greater than E2, we need to pull the first term from the first summand, right? We need to pull it here, and in the tail, we have the tail of the first summand and complete form of the second summand. So the second case is just symmetrical. And the last case is when exponents are equal, we just pull both coefficients and add them. So what is the problem with these definitions? The problem is they reference themselves, right? So for example, here, the definition of negation reference negation in the right-hand side. Here, this occurrence is legal, right? Because C is a multi-series in a smaller basis, so we can just apply recursion to justify this self-referencement. But this occurrence can be justified by recursion. What we need here, called co-recursion. Let me introduce it briefly. So some type theories, for example, Koch type theory, contain they have co-inductive types, and co-inductive types are used to model possibly infinite object we compute with in a lazy way. For example, stream is a type of infinite lists. Seek is a type of possibly infinite lists. And lint type theory doesn't have them. They can be modeled. So there is, for example, a construction called QPF that allows to embed conductive types into length type theory. So this can be workaround. But let's move on. Okay. So inductive types allows us to use recursion, and conductive types allows us to use co-recursion. Like recursion, co-recursion justifies some self-referential definitions. And as well as recursion, co-recursion may be primitive or non-primitive. So let's start with the primitive case, which is sufficient for addition and negation. Suppose we want to define negation on streams like this, just stream of real numbers. We would like to define it like this, but we can't, of course, because lin. So the second neck here is in the same basis, so you can apply recursion here. What we need to do is to rewrite this definition using recursion. So any inductive type has a recursor, as well as inductive types have recursors, right? So we just take this part and copy it here. Then we take this part and copy it here, and put this all together into this recursor, and we obtain a definition for which you can prove a theorem that true definition of this neck holds, right? So what is a primitive recursion? Primitive recursion allows us to define, for example, streams here in that form. So the form, and to be precise, the form is the following. We allow arbitrary head of the stream, and we allow the tail to be the application of negation to some new argument. And the important thing here is that the main operation in the tail must be the operation we are defining, right? So, for example, here we have negation as a main operation in the tail, and here we have an addition as a main operation in the tail of definition of addition. This is what we need to be able to rewrite it using a recursion. The problem is that not all operations we need are primitively recursive. For example, multiplication isn't. Yes, again, here's too many formulas, but I need to say that to define multiplication, we need to introduce an auxiliary operation, multiplication by monomial, and define multiplication by mutual recursion with that operation. So multiplication by monomial is defined like this. We just multiply all coefficients by c and add e to all exponents. And multiplication is defined like this. Again, it looks scary, but actually it's just this identity rewritten in the language of multiseries. The real problem here is that this definition is not primitively recursive because the main operation in the tail is not multiplication, it's addition. So to deal with this, we need to extend the class of allowed recursive definitions. So primitive recursion allows us to define sequences like this, right? The missing piece here is a notion of a friendly function. Yeah, this is a terminology from the paper, I believe, extensible recursion. It's again about Isabel. So I just ported a small fraction of it into Lean. So a function from sequences to sequences called friendly when to compute first n elements of the result, it needs only first n elements of the input. Right. It's not actually easy to define precisely what that means, but let's skip this part. So the main thing here is that now we allow this part foo tail arc be so-called guarded by the application of f. And it turns out that both addition and multiplication are friendly operations, so we can using this theory, we can finally define multiplication because addition is friendly, and the second argument here is multiplication as we needed. So let's move on and define the next operation, power series. For example, we let h be a real function that is analytical in the neighborhood of 0. Suppose we have an expansion of it into a power series, and we can substitute a multi-series into this analytical function. So the definition here is simple. I don't know. The main thing here is that in the tail we again use not pose there but multiplication, and multiplication is friendly, so we can do it. Yeah, and here we have a stronger precondition for theorems like I said on the first slide. We need for that operation to be correct, we need the function tend to 0. So we need the leading exponent of f to be negative. Using this operation, we can define, for example, inversion. The idea here is simple. We take the expansion of, for example, this function into power series. Then we rewrite f as a function in the following form. So this term tends to 0. So we can apply. So we can substitute it into variable c in this series, and we just basically translate this formula into the language of multi-series. And similarly, we can define powers. Yeah. We have only two operations left, logarithm and exponent. For them, we need to sometimes change our basis. So I need to introduce an additional structure we also maintain during the algorithm called log basis. Log basis is just a list of multi-series approximating logarithms of basis functions except for the last function. So, for example, if our basis is this, a log basis would be this, right? Because, for example, x log x as a multi-series approximates the logarithm of this function, right? Because logarithms and exponents cancels each other. And for using this structure, we can, for example, handle logarithm. So we expand our function as before, and we know that there are three terms in in the logarithm of f. The second term is just recursion. So to compute the multi-series approximating this function, we just use recursion because C is approximated by some multi-series in a smaller basis. The last term is just can be handled by substitution into a power series because again this term tends to 0. The only problem is the first term. Here we have two cases. If b is the last element in the basis, we just take the approximation of this function logarithm bx from log basis, right? Because it's not the last function. If it's the last function, we append log b x to the basis and bx to the log basis, right? Because of course bx as a multi-series approximates log bx logarithm of bx, right? The last element of the old basis. And the last operation I'd like to discuss is the exponentiation. So here we have three cases. if E is negative. So in this formula, we know that f tends to 0, so we can substitute it into power series for x. If E is 0, this is similar. We can just rewrite it like this. And this is a recursion. And this is a power series, can be handled by power series because f over line tends to 0. The only non-trivial case is when E is positive. And in that case, we compare f with elements of the log basis. By compare, I mean asymptotically. So by comparing tuples of their leading exponents. And if f in terms of this order falls between some elements of the log basis, we insert x by f into the basis and f into the log basis. Right? And this preserves all our invariants. So the basis is well ordered, the log basis approximates logarithm of the basis function, and so on. And if f is equivalent to some logarithm of basis functions, then we subtract it and recursively handle this exponent. And this recursion eventually will eventually terminate because this function is asymptotically smaller than this function, right? Because we subtracted something which was equivalent to this function. Right. So, and this is how we define operations. And then I'd like to discuss how we extract the hidden term. So, suppose we're given an expression for a multi-series, and we want to extract its hidden term. For that, we normalize the multi-series. So we basically simulate the lazy evaluation until we reach one of the normal forms, either nil or cons. For that, we use theorems like this. For example, if we want to normalize f plus g, we normalize f, normalize g, then we compare the leading exponents and use an appropriate theorem. For example, like this. We substitute all the information we collected into arguments of this lemma and rewrite using this lemma. Right? And this allows us to bring f plus g into the normal form. In that case, it will be cons. So we do it recursively, then with the coefficient, and after that we can easily extract the leading term. And by inspecting it, we can figure out the asymptotical behavior of the function.
Yeah.
All right, let me
Yeah.
conclude. Sorry.
So I was about to say you're almost out of time, but I see that you're not talking about conclusion, so that's fine.
Right. Sorry.
No, no
So let me
problem.
conclude with some lessons I learned during this project. First of all, I think we need co-inductive types in Lean, and we can see that there may be useful for applications outside of, for example, computer science. So here we use it for analysis, right? But it's not enough actually to be able to define co-inductive types. We also need a theory for general recursion, for example, to define multiplication operation. All right, and in the future, I plan to pair the tactic to Matlab. I hope I'll start doing it in a week or so by splitting this. This is quite a large code base, but I'll split it into smaller pieces and start pairing them and support more functions. For example, the Isabelle version of this tactic are more powerful. It supports, for example, sine, cosine functions and a gamma function, which is very useful, I think, in applications. Thank you very much for your attention. Now
Thank,
I'm ready to answer any
thank
questions.
you very much, Vasily. It was